Hello, this is a tutorial on the lithium-ion batteries. It follows on from a related tutorial on introduction to batteries. So the lithium-ion battery is a secondary battery, and the two electrodes of the lithium-ion battery, they are made from lithium-containing compounds. And furthermore, these lithium compounds are what's called intercalated materials. And later on we'll see that by intercalated we mean the material is in the form of stack sheets. So it's like a stack of cards. So why is that? The reason is because during the charging and discharging of the lithium-ion battery, the lithium ions will have to move from the positive to the negative electrodes and back. So you have lithium ions shuttling back and forth between the two electrodes, and you therefore need to use these layered materials to allow that process to take place. And another term which is often used to describe the lithium-ion battery is that it's a rocking chair battery. And this is for the same reason. You have these lithium ions shuttling back and forth between the two electrodes, so it's called a rocking chair battery. This battery was discovered in the 1970s at the University of Oxford because of some basic research, but since about 1990 it has become a standard energy storage device for electronics, as we will see. So this is an example of a lithium-ion battery. And in this table, we are basically showing the characteristics of the lithium-ion battery. And essentially, the left side, the left column of this table is showing the advantages, the strong points, if you like, for the lithium-ion battery. And the right-hand side of this table is showing the areas where the lithium-ion battery is still not so strong. So if we start with the advantages of the lithium-ion battery, we can see that this battery has a high specific energy. This is second from the bottom, and this means that it is able to store a lot of energy per unit volume, and this is why the lithium-ion battery is so useful for portable electronics. Other advantages of the lithium-ion battery include a fairly high power or rate of discharge, and it also has a low self-discharge rate. In other words, if you don't use this battery, it's not going to discharge within itself because of some internal reactions. Other advantages include a large number of charge-discharge cycles, ability to operate over a wide temperature range, and also there's no memory effect. That means if you recharge it to a slightly lower voltage, then the next time you recharge it, you are able to exceed that voltage. It's called a memory effect. Some of the better known limitations of the lithium-ion battery is that it's liable to thermal runaway. So that means if you inadvertently overcharge the battery, there is the possibility that the side reactions which will take place from that point onwards can lead to temperature rise, and eventually the battery could become damaged. And therefore you need to build in protection circuits and to prevent any venting of gas from the battery when it is overcharged. So this slide provides a little bit of background on lithium metal. So lithium has a chemical symbol of Li, and it's the third lightest element in the entire periodic table because it has an atomic number of 3. So there are just 3 protons in the nucleus of every lithium atom. And in fact, lithium is the first metal in the alkali series of metals. So lithium is therefore a small atom, and because it's small, it also has a very low mass density, and that's why it's difficult to store lithium. We find that lithium cannot even be stored under any liquid. It will float on water, and it will even float on oils. And like most metals, lithium is a shiny element, and this metal is mined from the salt flats in South America, such as in Bolivia and in northern Chile. Lithium electrodes. Just now we pointed out we need to store lithium in an inert environment, and that is because lithium itself is a very reactive element. So it will try to form a compound with another element, such as oxygen, very, very readily. This point is important because this is the reason why we are able to store a large amount of energy within the lithium-ion battery. So why is lithium reactive? The reason is because, like sodium, which is a related alkali metal, it has 1 valence electron. So this is an electron in the outermost shell of the lithium atom. And in that configuration, the lithium atom is very unstable. So it would always like to give up this electron in an oxidation reaction. And the amount of energy involved is quite significant. And so for this reason, the lithium-ion battery has a higher open circuit voltage than a typical battery. So it's about 4 volts as opposed to 1.5 or 1.2 volts for other battery types. So this makes this type of battery very useful as an energy storage device. So in this slide we will talk about the 2 electrodes in the lithium-ion battery. The positive electrode, or the cathode, could be made with various oxides of lithium and another metal. So the earliest one is the lithium cobalt oxide electrode. So these chemical symbols, CO, that is the element cobalt. It is a transition metal. And essentially the lithium cobalt oxide electrode is able to store a large quantity of lithium ions, and the lithium ions are able to diffuse through the layers in the electrode quite easily. And this material also has a good or high electronic conductivity. So the electrons are able to move through this material easily as well. Other characteristics for this electrode is that it will not dissolve in the electrolyte and is relatively simple to prepare. The other electrode in the lithium-ion battery is the anode, or the negative electrode. And this is typically made from graphitic material. So you can use graphite in the simplest case. And in the earliest product for this type of battery, amorphous carbon was used, but because it's not a layered compound, so the performance is not as good compared with using a graphitic material as the negative electrode. And like the positive electrode, the lithium ions are supposed to move through the sheets, move between the sheets in the negative electrode. So in this slide we will look at the electrochemical reactions which take place within the lithium ion battery. So first on the positive electrode, we can see that the chemical reactions has double arrows. So this shows that this type of battery is a secondary battery. So it can be charged and it can also be discharged. So if we first of all look at the discharge of the lithium ion battery, we can see that what happens is that during the discharge, the electrode is being reduced together with the lithium ions back to the LiMO2, that is the lithium metal oxide. So notice that the M is a transition metal such as cobalt, but it could be other transition metals. When we discharge the lithium ion battery, a corresponding reaction will take place at the negative electrode or the anode. And this is shown by the right to left reaction on the second line. So what happens now is that the lithiated graphite electrode will be oxidized to carbon and lithium ions. And the lithium ions basically will move back to the positive electrode. So this is what happens during the discharge. And for the charging cycle, right, everything is reversed. And this is shown by the left to right arrow in these two electrode reactions. If we combine the two reactions, we will obtain the overall reaction. So you can see that we have LiMO2, we have graphite, and they can be turned reversibly into lithiated graphite and also the lithiated transition metal oxide. In the next two slides, we will use a simple animation to show the lithium-ion battery processes. So in this slide, we are showing what happens when we charge up a flat lithium-ion battery. So essentially, during charging, we are connecting an external voltage source to the lithium ion battery, and the lithium ions will move from the positive electrode through the separator in the middle, and is within the electrolyte, to arrive at the graphitic negative electrode. So the lithium ions, which are the red dots, will be moving from the left of the slide to the right hand side of this slide towards the negative electrode. So they will position themselves between the planes of the graphitic electrode. This slide shows the discharge process, and in this slide the lithium ion battery is being used to power some external load, and basically the reverse happens. So the lithium ions will now move from the negative electrode to the positive electrode, and because of the electrochemical reactions, you will get an electron current from the negative electrode to the positive electrode. The symbol V at the top of this slide represents a voltmeter. So what it's trying to show here is that when we discharge this lithium ion battery, we are able to measure a terminal voltage by the voltmeter. This slide shows a little bit more detail about the microstructure of the lithium LiMO2 cathode, and this relates to what we mentioned at the first slide. It shows what is called an intercalated compound. So essentially this LiMO2 material is in the form of sheets, and each sheet consists of an octahedron of metal and oxygen atoms. So every sheet of the LiMO2 cathode is basically like a little crystal, and this crystal consists of these octahedra. So you have an oxygen atom at the vertices of the octahedron, and in the center you have some transition metal M. There is some space between the adjacent sheets in the MO2, and the lithium ions are basically situated between adjacent layers in the electrode. So some examples of such intercalated electrode materials are the lithium cobalt oxide and lithium nickel oxide, and this is used in another battery which we will not talk about in this tutorial. So some of the applications of lithium ion batteries are very well known. For example, in the portable electronic devices, nowadays they are all powered by lithium ion batteries because of the high specific energy. And a more interesting and more recent application is that they are also used as a power source for electric vehicles, including electric sports vehicles. So the example on the right is showing that you are able to get high speeds from an electric vehicle which is powered by these lithium ion batteries. So the lithium ion battery acts as an energy source for the vehicle, and the energy is used to drive the powertrain and also all the onboard electronics of the vehicle. This slide shows another emerging application of lithium-ion batteries, and it's what's called the grid-scale energy storage. And this is to do with these renewable energy sources. So for the photovoltaic panels on the left, and for the windmill on the wind turbine on the right, we can see that both these renewable energy sources, they are quite unpredictable. They are intermittent, and therefore it's very important that when the energy is available from these renewable energy sources, we must immediately store the energy. And at the moment, the typical battery we use for grid-scale electrical energy storage is the sodium sulfur, or the NAS battery. But this may change in the future, because the lithium-ion battery, through technological improvements, can eventually become an alternative to the sodium sulfur battery. So another interesting application for the lithium-ion battery is to act as an energy storage device for the future smart grids. So we summarize this tutorial. So the electrodes and the electrode reactions in the lithium-ion batteries have been explained in this tutorial. And we also touched upon the applications of lithium-ion batteries. These include mobile electronics and electric private vehicles. And in the future, the smart grid may make use of the lithium-ion batteries as an energy storage device for renewable energy sources. So this is the end of this session. I hope you have enjoyed it and found it helpful. You're most welcome to visit the website again and watch other video tutorials in your areas of interest. Thank you.